I have finally released the Arduino sketch for the SilverHat booster, so it's time to show you how you can build and configure this booster for yourself. Hello everyone and welcome to the IoTT channel. I am Hans Tanner. A special welcome to all new subscribers and welcome back to everyone else. I am happy you made it here and thank you for your support of my channel. The SilverHat booster can be built and configured in several versions, either for just DCC or combined with LocoNet, and it can provide track current to up to 6 layout districts with up to 8 amps track current each. In this video I am going to show how to build and configure a very simple version, a DCC booster with just 2 output channels. In one of the next videos I will then show how to build the LocoNet version along with the additional configuration options. If you don't want to miss this and any other future videos, it is a good idea to subscribe to the IoTT channel and activate the notification function. Let's get started with looking at the components needed to build this booster. First, an Arduino board, either an Arduino Uno or Arduino Mega. Then a PowerShield for each output channel. The PowerShield generates the DCC current that goes to the track. And finally, a Tinkercad shield to connect the DCC input. Looking at these boards, you might think that these are the same boards as you would need to build a DCC-X command station. So, is this the same? I indeed had this question being asked by some viewers recently, so let me just take a minute to explain the difference. In short, the command station is the brain of the DCC system. It receives the commands from the user and creates track commands for the locomotives, and as long as there are not many locomotives or other consumers connected to the command station, all is fine because it has a built-in booster as well. But if the layout grows and there are more locomotives or locomotives that draw more current, then the command station may reach the output current limit and it is time to add a booster to amplify the output current of the command station. So a booster needs the DCC signal from the command station, and all it does is amplify it so that more locomotives can be operated at the same time. From an electrical point of view, this requires very similar components. That is why the list of required boards for the booster is very similar to the ones needed for the command station. What is different though is the software that is running on the Arduino processor. If you load DCC-X, the board has all the smarts to create the DCC signal from your command inputs, while when loading the SilverHat software, all the board can do is amplify the signal and monitor the output for overload and short circuit. So let's build a booster for 2 power districts. The first board is the Arduino, either Uno or Mega. It needs to be loaded with the SilverHat software, which is quite easy to do. You can download the SilverHat software from the GitHub link listed in the description. If you want, you can download the source code and compile it for yourself. Or you can download just the executable hex file, either for the Uno or the Mega. If you choose the source code option, you load the sketch into the Arduino IDE, compile it for your board type and upload it to the Arduino. If you do not have experience with the Arduino compiler, you can download the executable hex file for your Arduino type and the xLoader software. The download links are in the description as well. You unzip the xLoader file and start the xLoader program. Connect the Arduino to a USB port, select the SilverHat text file and the Arduino board types. Then select the serial port the Arduino is connected to and click on Upload. It takes a few seconds and the Arduino board is programmed with the SilverHat firmware. Before we install the PowerShield board, it needs to be configured for the correct I/O pins. The DCC signal is coming in via I/O pins 2 and 3, so we need to set a wire bridge from pin 2 to PWM1 and from pin 3 to PWM2. If you are using an Arduino board with a USB Type A connector, make sure that the configuration wires do not stick out on the bottom side of the PowerShield, so that they do not touch the body of the USB connector, which carries ground potential. It is also a good idea to place a piece of electrical tape on the connector for some extra protection. I recently found some Arduino boards featuring an USB-C connector, which of course eliminates the risk. Next, we set the signal selector jumper to the PWM2 position. This means that the output will be driven from the two DCC input signals on pins 2 and 3. Finally, we have to set the wire bridges for the current sensor on the analog input field and for the power enable pin. If you want to use the auto reversing feature, you also have to configure the AR pin. If not, there is no reason to configure it. Here is a table with the recommended pin numbers for the maximum of 6 power shields that can be supported by one single Arduino board. Basically, you can choose any pin you want except for pins 0 and 1, which are used for serial communication, and pins 2 and 3, which are used for the DCC signal. If you plan on using Loconet later on, you should also avoid using pins 6 and 8 as they are used for Loconet communication between the IoTT stick and the Tinkercad shield, but that will be covered in the next video in more detail. So, as shown in the table, that leaves you with I/O pins 4, 5, 7 and 9 through 13 to be used as power or auto reversing pins, and of course the 6 analog pins for current sensing. Following the table, you can build a booster with a maximum of 6 boards, 2 of them in auto reverse mode, or 4 PowerShield boards and all of them working as auto reversing outputs. Once the PowerShield is configured, it is placed on the Arduino board. Make sure all pins are inserted properly and there is no contact between the USB connector housing and any configuration pin. If you want to use additional PowerShield boards, configure them the same way and simply stack them up. Finally, we place the Tinkercad shield on top of the stack. Make sure it is configured for DCC input, so the jumpers for pin 2 and 3 need to be set. The jumpers for pins 6 and 8 remain open. The pins to configure the stick interface and Loconet do not matter in this application, so just leave them unchanged. With the hardware built, the booster is almost ready. All we need to do is configuring the software for the selected I/O pins. To do so, you download the SilverHat Configurator tool from the GitHub page and unzip it. You then double-click the index.htm file to open the configurator in your web browser. Make sure your booster is connected via USB connector, then click the Connect SilverHat button and select the port the booster is connected to from the list and click the Connect button in the dialog. Wait a few seconds and the current settings of the booster will be displayed. After the first startup, the pin numbers will be assigned as shown in the table and the number of booster modules is set to 1. Use the drop-down selector to change the number of modules based on the number of power shields you have added to the stack. The sensor rate is set to 12.2 as needed for the PowerShield revision 5 and higher. If you are using an older revision 4 PowerShield, set this value to 8.31. The Loconet address is set to 1234 by default, and unless you want to use the Loconet feature and connect several boosters to the same network, there is no need to change it. Verify that all hardware settings are correct and make changes as necessary. Note that the changes are effective immediately, but to make them surviving a reboot of the SilverHat, you need to click the Save to EEPROM button. Finally, connect the DCC track output of your command station to the DCC input of the Tinkercad shield, or if your layout uses Loconet, you can also connect a Loconet cable into one of the Loconet sockets. Make sure your Loconet cable carries the track signal on pins 1 and 6, which is normally the case if it is connected to another booster, a command station, or another socket of Loconet B type. If the DCC signal is received properly, the input signal string on the configurator will change from no input to DCC, indicating that the valid DCC signal is received. Now it is time to connect your power supply. Make sure the selected power supply can deliver enough current for your layout. Ideally, the nominal output of your power supply should be about 20% higher than the booster current you are planning to configure. So if you want to have a 5 amp booster, your power supply for the channel should be able to deliver about 6 amps. It is also possible to connect a single power supply to more than one PowerShield, but the same rule applies for the sum of the currents. So if you plan to have 2 PowerShields set to 5 amps each, your power supply should be rated 12 amps or higher. Also, watch videos number 138 and number 141 for more information about choosing the right power supply. After connecting the power supplies, it is a good idea to perform a short circuit test. In order to have a safe setup, it is important to make sure the power supply can deliver enough current to reliably detect a short circuit and shut down the track power. To perform the test, click the Measure button in the Short Circuit Test column. The booster will shut down the track output so that it is safe to connect the 2 rails to create a short circuit connection. A new confirmation dialog window appears on screen, and when you are ready, you click the OK button to perform the test. The booster will switch on the track power for a few milliseconds and measure the short circuit current during that time. The value is then displayed on screen and helps you to determine the maximum current you should set for this booster. When you are done with testing all booster modules, click Save to EEPROM so that the values are properly stored in the booster. Now you can use the Options tab to set more configuration values for each booster channel you have installed. First, you can select the track status after powering up the booster. Note that this value impacts all installed modules. Set it to On or Off. Next, you set the nominal current for each installed booster. This is the current that the module will be able to deliver on a continuous basis without going into overload mode. If you measured the short circuit current, the configuration page will show a recommended value based on the short circuit current your power supply was able to deliver during the test. To ensure the protection functions of the booster are working properly, you should not exceed this value for your nominal current settings. If you want your booster module to work in auto reverse mode, click the checkbox. Then select the reset mode for each booster module. If set to manual reset, the booster will shut down in case of a short circuit, and you will have to manually reset it to restore track power. In limited auto reset mode, it will try to restore track power for a few times and then, if the short circuit remains, permanently shut down and wait for you to reset it. And in automatic reset mode, it will keep trying until the short circuit is removed and track power can be restored. The fuse mode drop-down box lets you determine how fast the booster reacts if a short circuit occurs, and also how long it will tolerate a current flow that is higher than the nominal track current you have set. You can try to set a predetermined characteristic from very slow to very fast, or you can experiment with your own value settings if you prefer. Higher values will make the booster react slower, and values should be multiples of 10. Again, like with all the other configuration settings, click the Save to EEPROM button to store them in the booster and make them permanent. Okay, that's it for the configuration. Now we can connect the track output, run the trains and use the Monitor tab to see what's going on and control the booster as needed. On the Monitor page, the status of the input signal is displayed as well, so you can immediately see if the booster is receiving the DCC signal. The next two buttons allow you turning the track power of all booster modules on and off. The actual track current consumption can be seen on the current gauge. The end of the green range indicates 80% of the nominal current. So if the nominal current is set to 3000 milliamps, the green range ends at 2400 milliamps. Yellow indicates that the booster is quite loaded, but still within the nominal range. Light red means the booster is operating above the nominal range and will shut down for current overload after a certain amount of time, depending on the fuse settings. Dark red indicates the current is too high and you risk to reach the short circuit trip current at the end of the dark red range, which will shut down the booster immediately. The load factor of the booster is indicated in the next column, as well as the output polarity of the reversing output, if you are making use of this feature. In the last columns you have the buttons to toggle the output power of just one specific booster module, a reset button to reset the booster after a short circuit if it is set to manual or limited auto reset, and a button to actively change the polarity of the auto reversing output. Note that this button is only showing if the booster is configured for auto reversing. So let's add a track load. As soon as the current is flowing, the gauge shows the value in milliamps. Also, track status and booster status is indicated. The load factor display shows to what degree the booster is loaded. If the nominal current is flowing, the load factor is 100%. If the current increases, the load factor increases as well, simulating a thermal model for the device. It allows you to go to a maximum load of 120%. If that threshold value is reached, the booster channel will shut down and allow for cooling off until a value of 60% is reached. Then it will restore track power automatically, independent of the reset mode, which only applies for short circuit shutdowns. Of course, using the monitor screen requires the booster to be connected to a PC via USB port. The advantage of this is that the USB also provides power to the Arduino board. If you do not want to connect the PC during operation, you can operate the booster standalone. In this case, you need to connect a power supply to the barrel jack of the Arduino to power it. A 6-volt DC power supply is the best option. The disadvantage of this approach is, of course, that you can no longer see the booster status on screen, nor operate the input buttons for track power, reset and auto reverse polarity. It is therefore best to set the booster output to auto reset mode and set the power up state to power on. With these settings, the track output will always be on as long as there is a valid DCC input and no short circuit on the track. And of course, what always works is the track power indicator LED on each PowerShield board. To get rid of these limitations, you can equip the booster with an additional DCC aux port and an IoTT stick, which will allow you to connect via Wi-Fi and load the web page from your cell phone or any other Wi-Fi connected display. This is what I will show in the next video, so stay tuned. And that's it for today. I hope this information was useful or at least interesting for you, and I gave you an overview how you can build, configure and operate the SilverHat booster to meet the current requirements of your layout. If so, please use the comment section of this video to let me know your thoughts and click the like button below. That is an easy way to show you your support for the IoTT channel and to promote this video to other model railroaders, because YouTube likes the likes. Thanks for watching and see you in the next video.